So, as you may have noticed, I am not a teacher, I am a student. So if you are wondering what I have to share with you as a student, I'll go ahead and answer that question by introducing myself just a little bit. So I'm a student, I'm learning computer science at the Paideia school, but I also have some experience teaching computer science. I've created a Scratch curriculum, and I actually taught a course at my school on programming on the calculator. So same calculator you might use for your math test. And what I loved about those was just finding those kind of programming concepts and finding ways to apply them in all different spaces. So what I've learned, kind of both learning computer science and some experience teaching computer science that I want to share with you, is just the importance of making the really magical parts of computer science very accessible. And so I hope that the VEX tool that I'm going to show you today will help achieve that goal. Thank you. Thank you very much. So the VEX playground is created by the same people as the VEX competition. So if you've heard of that, you're welcome to go ahead and say in the chat if you if your school participates in or you've heard of the VEX competitions. But in the spirit of accessibility, what I love about this tool is that you don't need to have heard of the VEX competitions. You don't need to have anything. You don't need to download anything. You don't need to buy anything. All you do is click on the link. It's just like Scratch, and you can get started. So the first link I put in the chat, the vr.vex, is the link to the playground, and like Scratch, you can get started immediately. However, there's also these pre-built challenges on the VEX site, and if you want to see those, that will be my second link. And just a brief introduction to the program before I start screen sharing and go through one of my favorite little challenges. The main way to program in the playground is using blocks, just like Scratch or Snap, but you can also use Python code, and what I really love about it is the way it lets you transition from blocks to Python. You're able to convert your code and look at your code as you're creating it with blocks, how it would be written in Python. So if, as a student, you feel like you understand blocks well because they have this nice structure where you can drag and drop them, move them around, and they snap like Lego pieces, but you're intimidated by writing your first more complicated text program, this is a great tool for making that leap from blocks to text. So I'm going to go ahead and, yes, exactly. And that was me too when I was younger, and even now as I kind of continue to work on learning more languages, I think that's definitely the hardest transition. So I'm going to go ahead and open this first link, and I welcome you to go ahead and join me in this project. So if you want to open that first link, you'll get the playground, and I'm going to go ahead and share my screen in just a minute here. I apologize, but this is my window for the link. I'm going to make it a little bigger. And as you can see, I've started out with Python code. That's just what the default was for me. But you can switch to block code, which is a great place to start because you can always transition back to Python. So the way to do that is you can go to File, and then you can go to New Blocks Project. And I'm just going to discard this default project. And so this is where you should be starting. And you have your block code. It's just like many other block languages where you have your different categories, and you have your same control code and everything else with your loops and variables and your functions, which are represented as blocks, like in Scratch, etc. I will also invite you to open the second link, and if you look at this link, you will see the different challenges that are made by the VEX site. And the first one that I want to share with you today is the disk mover. This is a cool one because it takes advantage of the fact that you can really visualize what's happening using this robotics playground, which I think is especially nice because this activity works well for whether you're doing virtual learning or in-person learning. And if you don't have something physical where they can actually use that actual physical thing, maybe like a robot, this still allows you to get that kind of hands-on experience, because as I'll soon show you, you can still see the virtual robot. So it allows you to watch your code kind of be executed in that moment. So what I'm going to go through is level 1 of the disk mover challenge. So I see the challenge described on this Google Doc, which I got from the second link. And I see the environment here, which shows some disks and some goals. And it says, use the robot's electromagnet to pick up and place 3 disks of any color into any colored goal. So I'm going to take 3 of these disks and put them in the goal. So now that we know our challenge, let's go to the actual code. So to start, since this is our first program, why don't we start with a hello world to test that connection between the program and the actual interface. And this will be a good opportunity for me to show you some of the features that I like about this tool. So to get started, we are going to go to Playground. So once you press Playground, that allows you to actually see the robot and everything else in the space. You can see our little robot here, and you'll also notice that here the disk mover playground is selected. If it starts out as one of the other playgrounds, for example, grid map, which is just your basic screen, the same way in Scratch you might have your very first screen with the little Scratch sprite, the little cat. That's the same idea. But we're going to start out with disk mover because that's the one that corresponds to the playground in our challenge. And it has our little disks here. But our first program doesn't actually have the robot do anything. So if we run it with this little arrow, we don't actually see the robot move, but we should see something in the console, right? So I'm going to go ahead and pull up the console, which is this little meter in the top right. And if I move our playground a little bit, as you can see, it did in fact work. We printed hello in our console. You can also see we have a little monitor for our variables and sensors for debugging our more complicated programs. But for now, we have our hello. We can clear and also restart and play again, and we see our hello. But of course, what makes this platform really special is that you can actually easily program the robot. So it's recommended by the VEX site themselves that we can go ahead and replace our hello world with a drive forward, maybe a more appropriate connection to the robotic space. So let's go ahead and run our new and improved hello world, which is drive forward. And as we see, our robot drove 1 square forward. 200 millimeters in this space represents 1 square. And as you can see, some of our variables here changed, specifically the location. It also updates us about some of our sensor values, which you can learn more about. You can also change the camera here. So I like using this view because you're able to see the robot in a little more kind of 3D sense and watch it move. So if we restart, we can go here and run our program and watch our robot move 1 grid tile forward. I'll also show you in the top right, the same place that we opened our console, we can also open these little code braces and we can look at our Python code. So if I'm a student and I am transitioning from blocks to Python and I'm intimidated by the Python code, I can work in blocks and I can just have a nice code viewer up while I'm working, and that will help me kind of ease into seeing what the Python code would look like. So I can see that when I have this drive forward, if I change this to, for example, 400, it changes this here. So it gives me an idea that I'm changing the parameter of this function when I'm changing this. So it lets me line up the blocks to the code. It gives me an intuitive idea of how the concepts I've already learned in blocks translate to text coding. But let's get started on the actual challenge. So let's say we want to move these 3 disks back into the space. Well, we notice that the first disk is 1, 2, 3, 4 squares away, and each square is 200 meters. So we can change our drive forward to 200 times 4. And feel free to follow along. If you want to jump ahead and try to grab those discs before I do, you are welcome to. So we have our first drive forward, then we're going to pick up the disc. But what if you didn't know exactly what code you needed to pick up the disc? Well, that's when this little question mark feature comes in, which helps you figure out what the little blocks do. I like this a lot because often when you're programming, you find you need a function, you don't remember quite which parameter it takes, maybe you want to look it up, but right now you have it all condensed in one space. So you get that idea of, oh, it's okay if I don't know everything in the language, I can always find it, but you don't have to worry about kind of looking somewhere else, you know exactly where to look. So I remember that I wanted to magnetize the disk, so I'm going to go to magnet. And if I'm not sure exactly how this block works, I can click on it under this question mark tab, and it tells me how to use it. It says boost attracts an object and drop releases. So let's try it out. So after I go over to this disk, I want to attract it, and then I want to move backwards. So I'm going to copy and paste this, and I'm going to reverse back, and then I want to release it. So we can go ahead and run our code. And one last piece I'll add is a increase in velocity, just so that you guys can watch it move a little faster. It hit 100%. Now we can watch our robot go, pick up the disk, and bring it back and release it. Awesome. So next, we want to grab that next disk. So we know we want to copy and paste, pretty much a similar idea, but this time we want to move 2 squares forward, so we'll add 400 meters. And of course, we want to do the same for the final disk to get that third disk into our space, add another 400 meters. Great, thank you. I'm glad that it's helpful. I definitely really love using this myself, and it's very easy to get started. So if I'm a student, I already know, I'll go ahead and run it, but I already know that there's something more efficient than this, right? One of my favorite ways as a student to learn something like functions is to actually feel like I need it. I think sometimes when you're first learning how to use maybe a function or a loop, a student like myself will say, oh, well, this is supposed to simplify my code, but I'm simplifying it by adding something more complicated. That doesn't make sense. But when you have a real problem that you're solving and you have to add all this code, and then just imagine once I want to get these other disks, I'm going to have to repeat this even more times, then the student is saying, oh, wow, I wish there was an easier way. And another little added addition is that the functions are called blocks. So if you've used Scratch, you know that the equivalent of functions is blocks, which only makes it all the more fun because it looks like you're creating your own thing when you create a block. So as you've guessed, I'm going to want to simplify my program a little bit because I keep going and retrieving a disk. I'm going to make a little block, just a function or method called getDisk, and I'm going to have it get a different disk depending on how far away the disk is in squares, let's say. So I'm going to make a parameter. And of course, this is a lot easier, I think, for students to first wrap their heads around, definitely for me, than maybe when you're making your first function in Python. But as you can see, the second I made it, I got my own function definition in Python, so I can kind of see what's happening. So of course, to define the function, we'll take the code we used to retrieve the disk. And just like in Scratch, we have operator commands. So maybe we'll take our squares, and just like we were doing before, we know that each square represents moving 200 meters. And now we can, of course, throw this away and apply our function. So we want to get the disk that was 4 squares away, and 6 squares away, and 8 squares away. If anyone wants to get ahead of me, you could also apply a for loop here around your function. But for now, let's go ahead and see the function run. Retrieves the disk that was 4 squares away. And something I also like about this that is true of Scratch as well is how it highlights the code. So you can see, well, the only blocks I have in when started are these 3 get disk commands. but I look at how it's being highlighted as it's running through the get disk block. So it's a great way to visualize the timing of the code and what's running at what time. But of course, we can make this even more sleek with the equivalent of a for loop. And if you use Scratch, you may know that they don't have exact for loops, but you can emulate a for loop with a repeat loop and a kind of manual iterator variable. So I want to generalize this 3 calls to get disk. So I'm going to repeat it 3 times. And what I want to be changing is a variable. I'll just use the my variable. And the first thing we want is 4. So 2 plus 2. And then we want to change my variable. Let's see if this works equally well. As you can see, the main code that's running is inside of this getDisk function. One of the other advantages of the highlight is that it shows you that even though this code is running, it runs so instantaneously that you don't actually see the highlight. I think one of the concepts I had to learn was that even if a code I had in place was run, it actually runs so quickly that you often don't expect it to be finished. Excellent, so our code worked again, and now we have this nice code that can be represented by just a for loop and a simple function definition, and it grabs our 3 disks. So if you wanted to go over this project with students, it won't be too hard for them to wrap their head around just grabbing those disks at first, but you can turn that same project into something that shows how to use for loops and functions here with our block definition. And now we can also see how this can be used in Python. So maybe if you're more advanced, you start in Python, or otherwise you could slowly kind of transition to Python. So if I feel ready, I could go ahead and convert my project to a text project. So I'll go ahead and click that, and I'll save. And as you can see, the code that we were seeing in the code viewer the whole time is now Python code. And of course, this code runs just as well. It's the code we already made. But one way I like to approach it is once we have the Python code, if you have some experience in Python, you can see how we can make the code more efficient. For example, the variable we created in the blocks, it automatically made a global variable, right? So an opportunity to teach about different types of variables and how we're using variables is that since this variable doesn't need to be global, it can just be local to the whenStarted function. We can go ahead and delete the my variable. And in fact, this variable, we don't even really need a formal variable here since we were just using it as an iterator for a for loop. So one way to make our code more efficient is to take away references to my variable and just create and just have an iterator variable in our for loop and just use that instead. We can also take advantage of some of the properties of the range function, which works the same way if you use like colons when you're creating a list. So we can start at 4 since our first disk was 4 squares away, and then we want to go to 8, but it's non-inclusive, so we'll go to 10 and count by 2s. So we'll go 4 plus 2 is 6, plus 2 is 8, and we won't include 10. And now we can get disk at I, and we have the same code that we had before, but it's a lot sleeker now that we've gone into Python and made it a little bit more efficient. I'll also get rid of this extraneous reference to my variable. And redo our code and watch our robot grab those disks again. Oh, looks like we have an error. Oh, these need to be commas because this is a function call, so these are parameters. It doesn't actually take a list. Now we can watch our robot grab those disks. Of course, it's the same code, but we can keep improving on it as we move from blocks to Python. We can also continue to improve the code from here. So if we want to restart, let's kind of work in Python and see how we can work through the challenge even further. Let's say we want to grab the next 3 red disks, right? But I'm going to be working in Python now. Well, the great thing about starting with Python with this tool is that the drag and drop aspects of the blocks are still present in the Python code. So it just takes away one of those extra barriers from transitioning to text when you don't have to worry about looking up the function if you don't remember it, or remembering the various functions. You can just drag and drop them the same way you can with the blocks, particularly the robotics functions, the ones that interact with the robot directly, that are pre-programmed into VEX. So let's say we want to, after retrieving the disks, we want to turn. We want to move 4 squares so we get to the red goal and turn again. So I'll just drag in a turn 90 degrees to the right, put it outside my for loop, and then we'll move forward. We want to go 4 squares, so 200 times 4, and then we'll turn left to position ourselves towards the disks. And note that this is super easy to get started with just by kind of choosing a couple of challenges that you think are appropriate for the students and have them get working on programs. And it can be a very short project if you just choose to do, for example, a first level of one of the challenges, but it can also be more advanced. And I'll show you some of the more advanced challenges just very briefly. I won't go through them, but just to give you an idea of the types of things you can do. So now our robot is facing towards the red disks at the end of our program. And if we want to fetch those disks, we can use the same for loop we used before. We might even want to turn this into a function in and of itself. And we can grab those disks. We'll run through. And while the robot is grabbing them, we can go ahead and define another function. Maybe we want to get all. How much direct instruction do you recommend? Mini lessons before each challenge? That's a great question, and depends on the experience of the students. So I think it's definitely important to know the general concepts. The way I like to do it is to make sure they have some experience with each of the specific kind of pieces of code they might use. For example, if a sensor is relevant, it's helpful for them to see code that uses that sensor. Or if the magnet, for example, is relevant, to see code that uses that magnet. And also examples of the conceptual things that they might need to know. If they need to use a for loop, they might want to see an example of a for loop. But from there, I think that it's really best to have them play with it. I feel like I've learned so much from just playing around with the challenges, and that's when you learn things like, how can I make my code more efficient, and how can I apply those things that I just learned. So I think the more of that and the more just the student is excited about it, the better. So that's my opinion on that. I appreciate the question. So our robot just grabbed all the disks, and we're going to make a get all disks function. And this one doesn't even need any parameters, so we can get rid of our parameter, and we can just throw in our for loop that we made, and throw our for loop. And we don't even need this wait. It actually puts that in originally as a fail-safe in your loops, in case you try to do something like an infinite while loop in a way that messes up the code, but we will avoid that. So we have our get all disks function, and we'll do that. And we'll also get all the disks here. And why don't we go ahead and move here? Even this could be a function as well, but we'll go ahead and do it manually first, and then we'll get all of the last disks and put them away. We can also actually, so we can speed up our drive velocity, and we can also speed up our turn velocity. So I'll go ahead and do that, because why not make it just a little bit faster? And feel free to type any questions in the chat. So this is text-based and blocks. So I showed the blocks at the start, but I'll be happy to go back to it very quickly at the end. So we actually started with a block program and we converted it to text. This is, it's a model of a VEX robot, but for example, one that would be used in the VEX competitions. But if you don't have experience with VEX, it's completely irrelevant. So you're able to use it regardless, and just a standard robot with some sensors and some other features that give it some more functionality that we can work on coding, as well as a little magnet. Okay, great. So if we do a little top view, we've gathered all the disks, and we can make our code even more efficient if we notice that we have our little shift code where it shifts to the right. We can make even that a function. So there's all kinds of ways to simplify. Pretty simple challenge. I'm going to make a function called shift right. Shift right. We'll go ahead and put our shift right code in there. And we'll shift right. Our code is being ever simplified. We can watch the robot from a top-down view, and we could even repeat this, right? We notice that this is being repeated a few times, so we could do, for example, look how short for a nice simple program. So, but of course you can get started with just doing all of this with the just moving and turning. So I like how you can kind of look at it at different levels and try it in different ways. Of course, there's nothing wrong with just starting out with a program that just grabs all those disks with 100 lines of code. And I think once you write all of this with only move forward and turns, you'll have a very natural reason to throw some functions and some loops in there as well. So I can also go ahead and briefly show the blocks. You can't actually convert from text back to blocks. It's only one way. So if you wanted to kind of look back and forth, you could. I would recommend probably sticking with blocks, and you can just use the code viewer. That's an interesting point. I haven't actually used the make code, but that's very interesting. So this is the block interface for anyone who joined a little later. You can see that everything we just had in code is represented in blocks. We have all of the robot-specific functions here, as well as our general control code with our loops, blocks for functions. We have our variables, of course. We used a variable briefly to kind of make a for loop, but program blocks and use. Yep, yes, that's my recommendation. Awesome. Okay, so I know we're getting towards the end, and I'll leave a little time in case there's any leftover questions. The one last thing I wanted to show is the other challenges that you can do. So this could be a first challenge if you want to go through it. I really love that one, but there's so many, and a lot of them are really good. So they range in difficulty a lot. So if you want a more complicated one in terms of what you're thinking about, you can create an algorithm to solve this maze. And we have the maze environment that I'll pull up very quickly. So you can make a dynamic maze solver. For example, a simple program for this could just go on the right side of the wall and go to the end, but you can make a more complicated program that takes advantage of sensors to keep track of walls and create a mapping of the maze and solve it from there. So there's lots of different ways to approach these challenges at varying levels of difficulty. And if you want a more simple challenge to just kind of get started and get your feet wet with the tool, you could do, for example, a basketball drills challenge, where on this one you're just going back and forth with your robot, and it's just a nice introduction to loops and moving the robot to get you started. Awesome. So if you have any questions, I would love to hear those, but I appreciate the feedback and the engagement so far. Awesome. Yeah, I'm happy to answer any questions, but thank you very much. I appreciate it. I have thank you. I definitely think that, as we learned in the introduction, just feeling, once you feel at home with computer science, by having projects that you feel like you can have some control over, you see what's happening, you're like, wow, this is my space, then it makes you feel a lot more confident, and you can work through those challenges, and when something goes wrong, then you want to kind of keep going. So I like this a lot because you can see what's happening, you can feel like you have a good understanding. I know we're ending off pretty soon, but any last minute questions? Thank you so much, everyone who asked questions and was talking. And the links, of course, are in the chat at the start, so feel free to use those links. Pretty simple to get started. You can just go to a link and get started right away. I know the session's ending now, but thank you for everyone who came. I appreciate it. Let me know if you have any questions also about using the VEX VR code playground. I'm happy to answer. Thank you. I know it's time for closing remarks, so thank you. I'll go ahead and head over there.